Okay, welcome to video 2 of our nuclear power lecture. Today we're going to talk about the technology and how we control the rate of reaction to extract continuous power. Okay, so during fission, remember, which was the decay of uranium-235 consisting of protons and neutrons, and it splits in half, generating two new largish atoms and several protons. So several neutrons that are high energy. So these all have significant kinetic energy, right? They're flying away at very high speeds. There's also a release of some electromagnetic energy in this process. Okay, but the real contributor here is these particles with extreme kinetic energy impact other atoms and other particles, and they bump into them, and then these bump into each other, and before you know it, we've changed this kinetic energy into thermal energy. So fission results in thermal energy. So we're going to use this thermal energy to generate power. And we've known how to do that for a while, right? Using something like the Rankine cycle or a coal power plant. But now instead of burning coal, we're going to cause uranium to go through the fission process, generating heat, which will replace the boiler in our coal power plant. Okay, since we've already talked about the Rankine cycle and about how all of that works, we're just going to talk today about the one unique piece of technology to nuclear power plants, which would be now the reactor, or the piece of the technology that controls our reaction rate, using it to transfer heat into the working fluid of the actual Rankine cycle. It also serves a unique purpose, given the fact that all of these particles are very bad for you, that it protects the external environment from the dangers of radioactive decay. All right, so let's talk about a few parts of the reactor. All right, so the first thing we need to do is protect people from all of the high energy particles being emitted, and this we do with a giant piece of concrete, because that can absorb all of the particles very well. So here's a concrete shield. Okay, we have going in and coming out some what we will call coolant, some fluid that is going to remove the heat generated by the decaying rods and bring it out for use for something. In almost every case for power generation, it's to create steam so we can run a power cycle. Okay, but how are we getting that heat? So we have these rods of fuel, generally pellets of uranium oxide, which are stacked really tall in these very, very thin rods. And these rods are placed down inside of the reactor core. So this is a fuel rod. Okay, now we're gonna let's just define these on the next slide. So the fuel is a uranium rod with about 2 to 5% U-235. Remember, U-235 is actually our fuel. The remaining 95% of U-238 isn't really going to be used because it's not fissible. U-235 is fissible. Okay, and this rod is going to be replaced about every 3 years. Okay, cool. And then we've already talked about the coolant, right? And so the coolant removes the heat from the decaying rods for use with the Rankine cycle. Okay, we're going to come back to that because there's an important thing we do with this fluid sometimes. And that is why we're going to talk now about an item called the moderator. So this kind of just generic block I've drawn is the moderator. So remember we talked about how we need actually low energy neutrons in order to sustain a reaction. Well, what the moderator does is it slows down the neutrons. It doesn't stop them, it just slows them down. And what that does, remember we need slow neutrons, it maintains the reaction. Okay, and generally moderators can be something like heavy water, which is water with an extra neutron on the hydrogens, or just standard water, or even carbon existing as graphite, carbon sheets. Generally, water or heavy water are used because we need a coolant anyway. So the coolant is often the coolant plus the moderator. So in the type of power plant I'm about to show you, the coolant and the moderator is served, both functions are served by the water inside the reactor. Okay, and there's one more thing. Another type of rod. This is called a control rod. It is not made of uranium because generally a reactor, you want to build it and kind of space everything and have the contents of uranium so that it would have a runaway reaction, because you need to maintain your reaction. So you want to make sure you have enough sustainment of your reaction, but you don't want it to run away, so you have a control rod. And a control rod, we'll just call it the control, is some neutron absorbing material. And you're able to control how much of that rod is inside the reactor core at any time. And what this does is it slows down the reaction rate. You do not want this reaction to get away from you. As it decays more and more, it gets hotter and hotter, causing it to decay faster, more fission products to generate, and pretty soon you have this giant melty mass of metal that's going to just start sinking into the earth. Okay, so just a couple notes about the reactor. We already talked about it, but the reactor is encased in thick concrete. And that is to absorb any excess particles that might escape from the actual reaction. Okay, and then just for some numbers, a typical nuclear plant is going to produce about 3 gigawatts of heat. Right, these are all, if you're going to go to the trouble of building all of the containment measures for a nuclear reaction, you're going to build it big. So you've got 3 gigawatts of heat, which gives you about 1 gigawatt of power. And a power plant of that size will go through about 100 tons of fuel per year. A lot of that fuel, though, is reused. The actual amount of that fuel that is U-235 is going to be 2 to 5% of that number. The remaining, 95 tons of U-238 is actually used over and over and over again. It's just U-235 that must be replenished. All right, well, let's talk about types of reactors. I'm only going to describe one in detail because the others can be inferred. And I'm going to just tell you the most popular one, which is the light water as opposed to heavy water. So this is just normal water reactor, sometimes called a pressurized water reactor. Or a PWR. Okay, so we have the core. The core is what I've drawn here. This is the core. So we have a core. It's got the control rod sticking out. And then we've actually built around it a pressure vessel. So this is a pressure vessel. And on top of the pressure vessel, we've built an extremely thick concrete slab. You won't believe how much concrete exists in a nuclear power plant. And this is just another layer of protection, shielding people from the core. Okay, so we've got inside this pressure vessel, we've got some water. This water is going to go through a loop. And there is a pump circulating that water. And then that water goes into another vessel. Okay, and so in here we have pressurized water. And I mean very pressurized, like 100 atmospheres. We've pressurized the water to the point where it won't boil. It is so pressurized that it will remain as liquid water, even as we add extreme amounts of heat to it. And we're doing that so that we can increase the rate of heat transfer, right? We need a significant Q. We will get a very, very good rate of heat transfer if we have a lot of water, not steam, moving through this system. So that water goes through this cycle, and then here we have liquid water coming in, and that liquid water exchanges heat with the working fluid, also water, of our reactor, and then it leaves as steam, and this goes to the Rankine cycle. So we have two fluid loops. We have the internal pressurized loop, which is always liquid water, and then we have here the actual evaporator, which is evaporating our Rankine cycle working fluid. Okay. Yeah, so that's how the pressurized water reactor works. Okay, the next other most common form of reactor is a boiling water reactor. I'm not going to draw this because I essentially have already. We just need to take out a part. So this is just like the pressurized water reactor, but with only one fluid loop. So you see here how we had in a pressurized water reactor a single, always liquid loop transferring heat to our actual Rankine working fluid. Well, in a boiling water reactor, we abandon this second heat exchanger, and this fluid actually just goes straight to our Rankine cycle. So we're using radiated water in a turbine. It's great. And this is called a boiling reactor because we actually are boiling the water, which is still a super efficient heat transfer process. And then we have steam that's leaving it going straight to the Rankine cycle, and that is steam. So that is a boiling water reactor. Not as popular, but between PWRs and BWRs, you've covered almost every reactor in the world except for exotic ones that are newly developed or ones they have in Russia. Okay, last thing we got to talk about is exhausted fuel. So like I said, a fuel rod's going to stick in that reactor for 3 years and then it is spent. And a rod is spent once our U-235 ratio, which started at maybe 3.5%, that's the typical ratio for a PWR reactor, once it's decayed back to natural levels. Once it's decayed, then we leave the fuel for several years to let most of the radioactive waste kind of decay. Then we reprocess the fuel. Okay, and what we mean by reprocess is we reuse all of the U-238, and then we add more U-235, which we've refined from natural U-238. There's also plutonium, which is used as fuel for newer reactors. Plutonium is not a natural occurring element. We generate that inside of a nuclear reactor and then use it as fuel because it also is fissible material, which is great. But then there's essentially what we call radioactive waste. These are the smaller kind of byproducts of fission, which we can do nothing with. And it is radioactive for a long time. And this is kind of the big debate, is not what do we do with these. The big debate is what do we do about the plutonium and the radioactive waste, because plutonium turns out makes a very high yield nuclear weapon, and then radioactive waste is dangerously radioactive for a very long period of time. So that kind of makes this a very complicated technology, which we're going to talk about next when we talk about how this is currently utilized in the world and a little bit about the troubled history of nuclear power.